Hi everyone, thank you for your interest in my talk. I want to thank the organizer and reviewing committee for giving me the opportunity to present our latest findings. Recently, we are working on the discovery and validation of serum metabolites associated with whole grain consumption using a non-targeted metabolomics approach. My name is Stefania Noerman. On behalf of my co-authors, we are happy to share the updates with you in this online meeting. First, we know that the consumption of diet rich in whole grain has been widely recommended across various dietary patterns, such as Mediterranean diet, Nordic diet, etc. Epidemiological studies have repeatedly shown inverse association between whole grain consumption and the risk of metabolic diseases, such as type 2 diabetes and cardiovascular diseases. When we examine the effect of whole grain intake on metabolic health, there are some other factors that may surround the habitual whole grain intake. These factors may easily confound the association between whole grain consumption and metabolic health. For example, some epidemiological studies have shown that people with whole grain consumption also tend to be more physically active. We know how physical activity benefits cardiometabolic health. So, if we don't control for physical activity, the observed effect of whole grains on individuals may also be influenced by how active they are. Hence, it is important to exclude the effect of other confounding factors when we try to find the metabolites associated with whole grain consumption. Therefore, in this study, we aim to identify fasting serum metabolites associated with whole grain intake independent of potential confounders. The samples that we used for this study were taken from two subsets of Kuopio Ischemic Heart Disease Risk Factor Study, or called KIHD. It is an ongoing prospective cohort with over 2,000 middle-aged men living in Kuopio and surrounding areas in eastern Finland. Both subsets were originally meant to elucidate the link between dietary adherence and the risk of developing metabolic diseases. The LC-MS run for discovery set was performed in 2018, and the one for validation set was performed in 2016. The LC-MS parameters and main findings have also been published. You can check the references cited here for more information. The discovery set used the LC-MS data from 364 participants, originally aimed to investigate the association between adherence to healthy Nordic diet and the risk of coronary artery disease. The validation subset originally aimed to check the association between egg intake and the risk of developing type 2 diabetes. This set contained 239 participants, but 39 of them have been included in the discovery set. So, the data from these 39 participants were excluded, leaving 200 participants for the validation analysis to ensure the independence of both subsets. The serum samples for metabolic analysis were taken during the baseline examination visits between 1984 and 1989. The data were then combined with the dietary data assessed by using 4-day food record. On the obtained LC-MS data, we performed data pre-processing. First, we did the pick-picking and alignment procedure using MS-Dial. The results were then exported to an Excel file, which then underwent further pre-processing in R. We used an R package called Notame to correct for the drift caused by the long LC-MS run. We used pooled sample called a QC sample that was spread throughout the run for this purpose. Then we cleaned the data by removing the signals with low quality. The cleaned data were then log transformed, centered, and scaled to prepare it for the statistical analysis. These steps were performed similarly for both discovery and validation sets. To select potential covariables in the association between whole grains and blood metabolome, we use a tool called Directed Acyclic Graph, or DAG. Here is the Directed Acyclic Graph we drew together with an epidemiologist. Using this graph, we check what covariables may stand between the whole grain intake and blood metabolome, as well as their relationship. For example, age may affect physical activity, BMI, and blood metabolome, but may not be affected by the whole grain intake necessarily. After we drew the relationship between each factor, the DAG tool then recommended what covariates to adjust. Based on this graph, BMI, age, alcohol and energy intake, physical activity, and smoking were selected as the potential covariates that we would adjust in the statistical models. After we got the normalized data from the discovery set, we performed multivariate variable selection using random forest to maximize the number of variables. 130 features selected by random forest were proceeded to the linear regression model. In parallel, we also performed correlation analysis to account for the potential misclassification in random forest. Using the covariates that we selected in the previous step, we built another model adjusted for the selected covariates, both in linear regression and correlation analysis. 112 features with FDR 0.05 for linear regression and 245 features with FDR less than 0.005 for the correlation models were subjected to feature annotation step. We used different cutoffs for linear and correlation models to get a reasonable and feasible list of features that we need to annotate. From this, we got a list of 270 shortlisted features that we next annotated to get the list of metabolites associated with whole grains. After we got the list of metabolites associated with whole grain in the discovery study, we checked if they were also present in the validation set. On the metabolites that can be found in the validation set, we checked their associations with whole grain using both linear regression and correlation analysis. We did not use random forest for the validation set because somehow it didn't work properly here. We also performed the adjusted univariate model for covariates. The metabolites with FDR less than 0.05 in both linear regression and correlation analysis were regarded to have validated association with whole grain consumption in this study. This Venn diagram presents how many metabolites were associated with whole grain intake in each step. In the discovery set, 142 metabolites were associated with whole grain. But after adjustment for potential covariates, only 67 of them remain significant. We looked for them in the validation set. 12 of them showed established associations with whole grain in the validation set. But after adjustment for the potential covariates, only 8 of them remain significant. Here we can see what metabolites are visible in the Venn diagram. At the beginning, a plasminogen called PCP180HODE, glutamine, gamma-glutamilated amino acid, and other carboxylic acids such as pyrrolidone carboxylic acid showed association with whole grain. But after adjustment, they lost their association. Meanwhile, aminophenol sulfate and tryptophan retained the association. The indole derivatives of tryptophan, such as indole propionic acid, indoxyl sulfate, and indole acrylic acid, as well as some betanes such as serine and norvalin betanes, retain their association. After validation in the validation set LPC190, PC17082, hydroxyisoleucine, and synapyl alcohol were significantly associated with whole grains. However, after adjustment, only 8 metabolites retained their associations. They were pipecolic acid betaine, tetradecanedioic acid, and some alkyl resorcinol glucuronides with odd-number chain length. This result hence may highlight the potential of these metabolites to reflect whole grain intake independent of adjusted covariates in this study population. Of course, in each level, we also observe some unknown metabolites. Particularly in the validation dataset, 3 unknown metabolites retain their association after adjustment both in correlation and linear models. We are currently running targeted analysis to get the MSMS data of these unknown metabolites to help us perform the better annotation. Since we got a hint that the alkyl resorcinols, betanes, and microbial metabolites may be associated with whole grain intake, we continue to check if other metabolites in these groups were associated with whole grains. On top of 3 alkyl resorcinols that retain its association with whole grains in the validation study, we also checked if we could find associations with other alkyl resorcinols. Some features have matching masses with alkyl resorcinols, but we don't have the MS-MS data to confirm the identification. These features, however, did not show to have the association with whole grain intake, either in discovery set or in validation set in this study. Besides pipeccolic acid betaine, serine betaine, and norvalin betaine, we also checked if we could find associations with other betaines. Unfortunately, we did not find any other betaines to be associated with whole grain intake in this study. And because only pipeccolic acid betaine retained its association after adjustment in the validation study, this finding hence may nominate pipeccolic acid betaine as the betaine with the strongest association with whole grain intake in this study. Among all microbial metabolites examined in this study, only hippuric acid showed a correlation with whole grain intake at the discovery set, but the association was lost after adjustment. We cannot replicate this finding in the validation set. On top of that, we also collected some other metabolites that have been previously associated with whole grains from published literatures. Among them, we found no association between these metabolites and whole grain intake in this study. Of course, it doesn't mean that these metabolites don't have any association with whole grain, but we just cannot find them in our study. In conclusion, we observed some novel associations between some metabolites, such as tetradecanedioic acid and other unknown metabolites with whole grain intake. We also established the associations between whole grain consumption and other previously reported metabolites, such as pipeccolic acid betaine and alkyl resorcinols. The retained associations after adjustment for selected covariates, both in discovery and validation datasets, show the potential of this metabolite to reflect whole grain consumption without being confounded by the selected covariates. This finding deems important to separate the effect of whole grain consumption from other favorable lifestyle factors that usually surround the dietary patterns. However, it is important to keep in mind that association is not a causal relationship. Besides the effort to identify the unknown metabolites, further investigations are still needed to check if these metabolites are causally linked to the potential benefits of whole grain on metabolic health. In this opportunity, I also want to thank everyone who has contributed to the study. Dr. Sari Hantunen, Professor Tomi-Pekka Tuomainen, and Dr. Tarja Nurmi from the KIHD cohort, Mia Reponen, Professor Seppo Auriola from the School of Pharmacy, who have helped us with the LCMS analysis, Anton Klovus and Dr. Marietta Kokla, who have helped me with the statistical analysis, the funders who have supported us financially, and you who have watched my presentation. If you have any question or input, please feel free to drop your question in the comment box, send me a message in the on-air platform, or via email. You can find my email address and my Twitter account in this presentation. Looking forward to seeing your comments and talk to you later. Thank you.